Okay. All right, so I know we mentioned this last time, but I don't think we actually looked at real examples of it. But the shortcuts, we talked last time about, why have we chosen octal and why have we chosen hexadecimal as like these important bases that are important to us in like the computer world. Binary makes sense. Computers like that. Decimal makes sense. Humans like that. So why octal and hexadecimal? So we mentioned it last time, but let's close the gap on that today. So I'll say octal here. All right, so the octal numbers, actually, we can do it. Octal, we can do it just as a single thing. So the legal octets, so these are the octets. That's 0 through 7. So that is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So this is a 0. This is a 1, a 2, a 3, a 4, a 5, a 6, and a 7. All right. Now, what does that allow us to do? It allows us to do something like this. I will use the secondary thing here. It allows us to do something like let's go this way. 2, 3, 4, 7 octal to binary. All right, so let's say I was asking you to convert 2, 3, 4, 7 from octal to binary. Up until this point, we would have first converted this from octal to decimal. Remember, we have our 2 patterns for conversion. And then we would use one pattern to go from octal to decimal. Then we would use our other pattern to go from decimal to binary. Well, with using octal and this knowledge that you can use 3 bits to fully represent every permutation of 3 bits exactly fits the octets for the octal numbering system. So that means we can say, well, what is a 2? A 2 is 0, 1, 0. What is a 3? A 3 is 0, 1, 1. What is a 4? A 4 is 1, 0, 0. What is a 7? A 7 is 1, 1, 1. So the binary version of this is 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1. So we could just represent each octet as its 3-bit equivalent and then put them right next to each other. And that is the binary number equivalent to 2, 3, 4, 7 octal. All right, so octal gives us that compatibility. Similarly, hexadecimal. So my hextets are 0 through 9. A through F. And we can represent these in 4 bits. So that's 0, 0, 0, 0. 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0 1 1 1 1 0 0 0 1 0 0 1 1 0 1 0. That's great. That's a 7, an 8, a 9. Just up to that for right now. So this is a 0, a 1, a 2, a 3, 4, 5, 6, 7, 8, and 9. So this is our 0 through 9s. Now let's go over to this side. And we'll say A through F. And we'll keep going. So this is 1 0 1 0. 1 0 1 1 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1. This is an A. This is a B. This is a C. This is a D. This is an E. And that's an F. So in 4 bits, exactly 4 bits, we can use the 4 bits through every single different permutation of 4 bits to fully represent the 16 unique hexstats of the hexadecimal system. This. So that allows us to do something like BAD hex to binary, where before we would have had to convert BAD from hex to decimal, which is 2989, and then go from 2989 decimal to binary. Well, now I can just write out that a B is a 1011, an A is a 1010, a D is a 1101. So this is 1011, 1010, 1101 binary. So you can go from hexadecimal to binary, and similarly, you can go from binary to hexadecimal very quickly, just to kind of show you that. There's a little trick with it. So if I say 11001111, just banging out some things there. Hex. One thing you have to do is you need to break it into 4-bit chunks, and you need to start with the right-hand side, because anything on the left, you'll see, I'm hoping that I didn't give it equal space. Of course I did. Let me just tap a couple other ones in there. There we go. We're no longer even. All right, so we have a binary number like this. So you start separating in chunks of 4, starting from the right. Now, when you get to the far left, you see we only have 2 extra bits left here, just because of the number of bits that we had. 10 is the same value as 0010. So you just pad it to get it to your the 4 bits. All right, so now we have 4-bit chunks from all of these. So 0010, that's a 2. 1110, we go back to our chart here, is an E. One zero one zero is an A. One zero one zero, another A. 1011 is a B. And 1110
E.
is an E. So this crazy long binary number is equivalent to 2EAABE in hex. All right, so that kind of is the follow through with the benefits of noticing that octal and hexadecimal are extremely compatible with binary in that you can fully represent their numbering system using 3 or 4 bits. And you know, so just to kind of really ram that home here, notice that I have written every single possible way of writing 4 bits next to each other here. And it just so happens that there's exactly 16 ways to doing it. All right. So that's why hexadecimal is compatible. For octal, I've done every single possible permutation of 3 bits. And it just so happens there's exactly 8 of them, which fills the entire octal numbering system. And we mentioned last time, but if we did need to go to another level, you know, because we kind of said, well, what's the benefit of hexadecimal over decimal or binary or something, is that hexadecimal allows us to represent large magnitude values in relatively small footprints. The number is more compact, so it has the same value, even though we're representing it in a different language, the language of hexadecimal numbers instead of the language of binary numbers. You know, and this last example really drives that home, right? This is the hexadecimal version of the number. This is the binary version of the number. The binary is more than twice as long, right? It's a lot more bits go into it, a lot bigger value in terms of footprint. So if hexadecimal would benefit us that way, so would base 17 or base 18 or base 19 or base 20. The specific reason we chose hexadecimal is because of its compatibility with binary. Okay, so our next possible base would be base 32, which we could fully represent in 5 bits. All right, so base 16 can be done in 4 bits. Base 32 can be done in 5 bits. So if we wrote every permutation of 0s and 1s in 5 bits, we would get the entire base 32 numbering system, which would be like A through pretty far down in the alphabet. I don't want to count it out, but you know, much farther than F, but not quite to Z. It was where it would get you to, maybe S or R or something like that. So in any case, go ahead, Syed. And you don't have to raise your hand because there's a decent chance I'll miss hand raises. Just scream out. Pretty
Sure.
informal.
So, Dr. Littman, what is the way to remember or plan something of grouping those numbers from 3 bits to 4 bits to 5 bits on any specific permutations that we are
Are
trying?
you asking like, how did I get all the permutations?
Yeah, not this
How did
series, but you mentioned just now that for 32 conversion of 32 bit,
Yeah,
so we group with 5 numbers, right? Instead of
correct.
4. So
Yep.
how do you have that list that for this specific base conversion we have to group these many bits?
Are you mean for 5 bits or why? I guess I'm still not understanding the question. So you're asking for a
Any kind of base conversion.
yeah.
How do we get to know that grouping these many bits would be ending up our result accurate?
Okay, so it has to do with the compatibility between binary and whatever that base is. So for instance, base 2 is obviously compatible with base 2. Base 4, which can be done in a total of 2 bits, that is compatible with binary. So we can write every permutation of 2 bits and be able to get the 4 numbers 0, 1, 2, and 3 for base 4. Then we have base 8, which, and all I'm doing here is counting. So this is 000, 001, 00010, 011, 10. This is just binary counting.
Sure.
Okay, but I chose 3 bits because I happen to know that 2 to the 3rd power is 8. So the math suggests that we'll be able to represent all those values. 2 to the 4th power is 16, which takes us to hexadecimal. 2 to the 5th power is base 32, whatever that's actually called, whatever name that guy has. All right. So things in between, if I chose base 9 here, and I got down, so I needed to then represent a an 8 and a 9. An 8 I can't represent in those 3 bits. I would have to go to that 1000 value, and now I'm outside of 3 bits, so it breaks the rules. And 1001. So no longer can I say, well, if I'm doing this in base 9, actually base 9 would just be to an 8. So I just barely break the rules, but it's good enough. It breaks the rules. Okay, so base 8 worked, but base 9 going all the way up to a number 8, legal values in base 9 are 0 to the base -1, which is 8. I can't represent 8 in 3 bits. I've already used every single possible way of writing 3 bits here to represent my 0, my 1, my 2, my 3, my 4, 5, 6, and 7. I no longer have any extra permutation without repeating one to get to number 8. So I have to add a bit, and now all of a sudden it's not consistent. We can't say, oh, this is compatible with binary, so that we can do this little trick. All right, so that's why after octal, the next one is the next power of 2. Octal's 2 to the 3, hexadecimal's 2 to the 4, base 32 is 2 to the 5. After that, we could say 2 to the 6th, which is base 64, works. But why would we not be able to do this for base 64? So if base 8 works, base 16 works, and I'm telling you base 32 works, why would base 64 not work?
A bit too long.
How many letters are there in the alphabet, English alphabet? There's 26, right?
26, yeah.
And how many digits do we have? 10? So after 36, we've run out of letters.
Exactly, sure.
Yeah. So, base 64 numerically works, but we don't have the language to represent it, right? We run out of the 0 through 9, A through Z. Now we need to come up with other symbols. Now we could create some sort of, table, like just make up symbols, have smiley faces and stuff like that, some emojis that represent some of the things. So as long as it's a single character, let's say, it would technically work, but human beings would start losing touch with this making sense to us, right? So that's why base 64 numerically works, but we don't have the language, the human language to stretch it. So, but good news is we're a pretty good distance from having to do that in order to represent things, because we're, again, we can accomplish base 32 right now. We have the, we're not doing it yet, but we can do it. We have the alphabet to be able to handle base 32. And if we're saying hexadecimal, if I'm just going to get a little bit, I already did this. I don't want to get too far into the weeds with this, but it is related to what we're going to be starting to talk about here with the data sizes. So when we think about hexadecimal is used for memory addresses. And I mentioned, I think a couple of classes ago, and just to kind of reiterate here, the coursework for this class is going to be mostly done through your reading and things like that, which I'll give you that again this week. So I'm mostly giving you kind of related, but filler information that's related to computer science that for those of you who've never had computer science or didn't have an undergrad in it or whatever, this is probably going to be new information to you. But for those of you who did have an undergrad in computer science, I'm guessing for many of you, this is also going to be new information because I'm going pretty deep into the weeds because a master's degree is more of a theoretical thing than an applied degree. So I'm guessing that this is new information for a lot of, or at least very rusty information for some of you who even have degrees in computer science. I just want to have everybody kind of feel like nobody in here is necessarily at a disadvantage other than maybe it's going to take you a little longer to catch on to the stuff I'm talking about. But the stuff I'm talking about in class here is supplementary information to what you're doing for the actual coursework, but also stuff that's going to help you build up your computer science skills towards the next courses, because I know many of you don't have a background in computer science. So that's just kind of truth in advertising what we're working with here. But if we think about when do we use hexadecimal addresses in our computers? We already talked about why we can use it. It's compatible with binary, right? So, base 16, very compatible with binary. We just proved that. So it's a good idea to pick base 16 instead of base 17, for example, or over base 15, for example. Okay, but now we pick, well, where does it really benefit us in our computers? And one area is we say it's memory addresses. Well, I think I mentioned a couple of classes ago that the way memory addresses work for human beings, which we take for granted, is far more complex than the way memory addresses work in computers. Right. So for human beings, you give your full, 123 Adams Street in hometown, Wisconsin, USA, zip code, yada, yada, yada. You guys are jumping to, other countries. So, our human addresses are pretty complex addresses. We have lots of different parts that let you zero in to where something is. In a computer, addresses are very simple. They just look scary. Okay. Everybody, if we think about our memory address as being a house, everybody lives on the same big long street. And we're just using hexadecimal, the base 16 number system, to label how far down that street you have to go to get to that house. All right. So hexadecimal is used for memory addresses. Now we have to give ourselves some sort of baseline. So let's assume back here, we'll give the worst case scenario. In our computers, this has to do more with the hardware side. So I'm not going to talk about that. We'll talk about that more in the 548 class when you do the mobile computer architecture class with me. In the mobile computer architecture class, we'll talk about kind of how memory works and battery life and crap like that. But in here, don't worry about how it actually works, but we have some choices in our memory, how much stuff we want to be able to store in each bucket of memory. How do we want to subdivide our memory? So let's just look at it in a worst case scenario and say that we're going to store exactly 1 byte of data at each place. And if you want to put that more into human terms, we're going to say that on this big street, we have a zillion houses and every single house is the identical size. It's 1 byte big. All right. So it's kind of like a little shack. All right. So every single house, identical size on this street. And we're just labeling this as that. This is house 0, house 1, house 2, house 3, house A, house B, house C, so on and so forth. We're counting in hex. All right. So if every single house is 1 byte big, that means we can have for 16 bits, we can have 2 to the 16th unique memory addresses. All right. So 2 to the 16th should be something like 4 billion, 0 to 4 billion. No, it should be 65,538. $65,000. So this means 65,536 unique memory addresses can exist. All right. So if we have one big long street, we have 65,536 unique addresses that we can represent. Not 65,537. If we have 65,537 houses, we need to go up to base 17. That's what we just saw on the slide over here when I was talking about the compatibility thing. Wherever it was when I was answering your last question. That once we went to the number 8, we went out of 3 bits, we went to 4 bits. Okay, so if we're stuck with a 16 base 16 number, which can be represented in 4 bits, we are stuck with a maximum number of unique memory addresses of 65,536. Now we can decide how much we want to store at each one of those addresses. And we can say that in the the worst case scenario, we can't store any less than this because just how memory works. We can store 1 byte of information at each of those buckets. So that means that we have 65,536 bytes of information. So unique memory addresses also means 65,536 bytes of info in total. Okay. So how do we put this into something that's meaningful to us? How much is 65,536 bytes? Okay. Well, and the cheating answer would be to say, well, it's 65,536 bytes. Okay. But that doesn't really give us values. As human beings using computers, we're not used to dealing with things in terms of bytes. We kind of know about bits, we know about bytes, but that's not how we count. You know, when you think about when you're downloading stuff off the internet, we're typically thinking about things in terms of megabytes or gigabytes, right? That feels like it has more meaning to us because that's how we measure the size of things in our computer. So if I flip over to this, so size conversion. We have bits and we have the bytes side of things. So 1 bit is a 0 or 1 is a bit. 1,024 bits is a kilobit, small k. 1,024 kilobits is equal to a megabit, small m. 1,000, or it's small m, small b as well, but you know, typically the small letters represent things in terms of bits, larger letters represent things in terms of bytes. And I'll kind of mention that here in a second. 1,024 megabits is equal to a gigabit. 1,024 gigabits is equal to a terabit. And we don't even talk about terabits at this point, but we could, and we could keep going if we wanted to. We can say 1,024 terabits is equal to what is the next one? Exabit. So whatever, but we'll stop there. That's far enough for us on that side. And this is going to be pretty similar to Syed's question about you can create this chart very easily. So you're gonna just by doing math like we did in the previous thing. You don't have to memorize these charts. You only have to memorize the baseline of them. So a byte, so 1 byte is 8 bits, is 1 byte. So to jump from this left-hand side to the right-hand side was a multiple of 8. Took 8 of these to get us to 1 of these. All right, now we just say the same thing as we did before. So we have 1024 bytes is equal to 1 kilobyte. 1024 kilobytes is equal to 1 megabyte. 1024 megabytes is equal to 1 gigabyte. And then 1024 gigabytes is equal to 1 terabyte. All right, so this is our size conversion thingy. All right. So now we might ask ourselves, how big is 65,536 bytes? Because as of right now, if we're saying that we have this many 2 to the 16th unique memory addresses, and we can only store 1 byte of information in each one, that's just a choice, a human being saying, well, I can only uniquely identify so many houses. All right, that's what this part says, 2 to the 16th. I can only uniquely identify 2 to the 16th houses. Now, I have to decide how big those houses are. Now, in real life, you go down that street, there's going to be houses of all sorts of different sizes, right? Okay, but in computers, we want to be able to be consistent, be reliable. So we're probably going to pick a size for all of our houses. You don't have to fill up the house with stuff, but everybody's going to live in the same size house. So in this case, the smallest house that can be built is a 1 byte house, a tiny house. All right, and we have 65,536 of those. So we want to get an idea of here, if we choose 1 byte of memory for our how our memory is broken down. That's the smallest thing we can remember in our system memory on our computer. 65,536 unique addresses gives us 65,536 bytes of information. Well, let's get that into either megabytes or gigabytes, things that mean something to us, probably gigabytes. So if I say something like 65,536 bytes to gigabytes, what is that going to be? Well, it's going to be 65,536 divided by 1024 will get us kilobytes, divided by 1024 will get us megabytes, divided by 1024 will get us gigabytes. So that is 0.00006. Maybe we should go to just megabytes. 0625. All right, so if we choose to use hexadecimal 16-bit values to represent our memory addresses, and then we also choose that we only going to store 1 byte of information in every one of those memory addresses, what are we stuck with? Well, we're stuck with a total computer maximum theoretical memory that we can store is 0.0625 megabytes. Probably not going to cut it, right? Modern day computers, that's not going to be big enough.
It has petabytes now, Dr. Little, maybe something more than petabytes of data.
We want to separate the difference between memory and, well, what you're talking about is we want to talk about the difference between system memory and system storage. So we're probably not at the point now where, I mean, I'm guessing somebody theoretically made this machine, but they aren't making machines with petabytes worth of system memory. You know, you go out and buy a computer today, your budget pleaser computers have 8 gigabytes of memory.
Yeah.
Oh, you go up a little bit, you get 16, 32, 64 gigabytes of memory is kind of our maximum amount on for machines that like people buy, right? Sure. Now you can go up to servers and crap that have like 2 terabytes of memory in them and things like that. But you know, we're in that realm for kind of maximum memory in a single machine. So what lets them make that decision? It comes back to how big are these houses? Okay, so with with 2 to the 16th unique memory addresses, that's the number of houses we can uniquely represent in our computer. That's it. If we choose hexadecimal to address our memory, that's our limitation. We can uniquely talk about 65,536 different places using the base 16 numbering system. All right. So with that in mind, we now need to decide, well, how big are each of those places to give us the ability to store more massive amounts of data. So maybe we say that, oh, well, maybe we're going to be like a 64-bit operating system or a 32-bit operating system. So this would be in a 8-bit operating system. That's what we would have. That would be total RAM.
And we have to remove one 1024 from the left side, right? So that because we are converting it to megabytes.
Yes, this is bytes, kilobytes, megabytes. Yeah. Okay. Now, really, I need to finish this off a little bit. Times 1, because we are choosing 1 byte for those guys. Okay. So how can we store more memory? Let's kind of work backwards here. Rather than do this, why don't we say this? In a computer today, we might say 2 terabytes of RAM is kind of our max for most of our hardware today. Okay, so 2 terabytes of memory, we need to decide how much total memory can be addressed by hexadecimal for 2 terabytes. All right, so let's get this into gigabytes. So 2 terabytes times 1024 gets us gigabytes. So that's 2048 gigabytes. 2048 gigabytes. All right. Let's get it even. Well, this is fine. So we have 65,536 unique spots. And we're saying that our modern computers, for whatever reason, can store 2 terabytes of information or 2048 gigabytes of information. So we divide that. So 65,548 divided by 2048. So that means that 32 gigabytes of memory can potentially live at every one of those addresses. So kind of like think of them like big mansions. Okay, that's if we're using the base 16 numbering system. Now, the reality is that our operating systems today, and like I said, we're not going to go too deep into this, but our operating systems today do tricks with base 16 to give us even more than 65,536 unique memory addresses. All right, they allow us to count in larger values. So actually, when we look at our memory addresses, a lot of operating systems today are like 64-bit operating systems. So you might have 8 hextets that represent the memory address. All right, so a single hexadecimal value allows us to do 2 to the 16th power. But we can bunch those together to represent larger amounts of data. But what I want to drive home here for us is that the size of each of those houses is what drives what we're talking about here. Okay, and those aren't decisions we make in this class. This is more of an operating system developer situation where they say, okay, we are writing the memory manager for this operating system. Our users are going to be doing this kind of work with our operating system, and the amount of data they're going to be working with is going to be X. So we need to make sure that we allow them to address memory adequately. So if we stick to 65,536 unique addresses with a single 16 base 16 number, we can put multiple numbers together to kind of have a more complex address similar to what we have in real life. You know, like 123 Adams Street, you know, Grafton, Wisconsin, yada, 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 that kind of stuff. All right, so that makes some sense. So this is our size conversion charts. This one chart goes from bits to bytes. And it's always a multiple of 1024. The left-hand side here is our lowercase bits. Now, generally speaking, human beings, when we talk about sizes and stuff, we're thinking about it over here for storage sizes. But when we're thinking about data rates, we often think about it in terms of those smaller case b. So I'll just leave us with in the last minute here today before I let us go. One pitfall people run into when I talk about like what your internet speed is at home. You watch the commercials for, you know, like around here, Spectrum might be your fastest internet. Although AT&T has fiber in the city of Milwaukee, but outside of the city, Spectrum cable modems are going to be your fastest. So when you buy their low plan, their cheapest plan from Spectrum, they'll sell it as 200 meg internet. Okay, it's actually megabits per second, not megabytes per second. So 200 megabits per second, you have to divide by 8. That gets you a maximum download speed of 25 megabytes per second. Same thing, AT&T's fastest internet, also Spectrum's, is gigabit internet. So that's 1024 megabit per second internet. You divide that by 8, you get 128 megabytes maximum download speed. All right, so this is one of those things that consumers are often misled, because obviously this kind of information here is not common knowledge to the consumer. A consumer might not necessarily recognize the difference between a megabit and a megabyte, gigabit and a gigabyte. Those things are kind of the same thing to them. They hear the word gig or meg, and those mean something to them, sort of. All right, but for us, as network, as computer scientists, specifically in a networking class, those data rates do mean something. If somebody says you have a piece of equipment that can download at 200 megabits per second, 200 megabits per second, that's the speed that it can download. And we have to put that in the context of something that's meaningful to us. Okay, and typically we think about things in terms of bytes. So we have to convert that to the byte side of things, divide by 8 in this case. And now we're at, oh, you have an internet connection that can download a maximum speed of 25 megabytes every single second. And I say maximum speed because, you know, you still are at the mercy of something else. And we'll talk more about that next time. All right, so any questions about any of that stuff we talked about?
Dr. Littman, I have a question. Can
Yep.
you please go back to previous slide? One more after this, 2031. Yeah, how we are deciding this as 8-bit OS?
Oh, because I just decided randomly. I kind of in the last few minutes been talking about how that decision about how big each of those houses is left up to the operating system designer.
Okay.
So if I'm an operating system designer and I decide I'm going to create an 8-bit operating system, that means that every single house is 1 byte big. 8 bits equals 1 byte.
Yeah.
Which is like not a practical operating system. You know, that's not going to be something that any of us are going to be able to work on, but it allowed us to see how little memory it allowed us to actually store at that level. Make some sense?
Yeah, got it.
Okay.
Thank you.
Okay, so you'll see a email coming out from me sometime today with like next week's assignment that'll be due midnight Sunday. We'll keep adding more supplemental stuff. I did see, I haven't checked Blackboard yet, but I saw many of you did email me last night with the assignments, so I'll start taking a look at them as well. So otherwise, I will see you here on Zoom at 8 a.m. on Wednesday, and we'll keep going. Sounds good?
Sounds good to me.
All right. Well, I will see you when I see you. Take care.
Thank you, Dr. Whitman. Take care.